Okay, so just to check, can everyone hear me and see the screen and all those things? Can everyone hear me? Okay. Okay, thanks. Okay, so the last time we were looking at this example on the drying of concrete, and if you've accessed the notes recently, you'll see that in the place where we've posed it as an exercise, there is a detailed solution there. And we had worked through all this last time. So we said the finite volume had that vertical thickness of delta Y, and into the screen was L, and across the page was W. And so that was the finite volume. And the area that the water was diffusing into was LW. And so we could get dc dt equals ddy of Na. And then for the flux, we had looked at the case of equimolar counter diffusion, but in the problem, it's talking about only the diffusion of water. And if we are assuming that the molecules in the concrete are staying fixed, then that's diffusion through a stagnant film. So let's expand on Na. So we know the standard form for the molar flux is given like so. And if we are diffusing through a stagnant set of components, then we can say that NB is 0. And that leaves us with this form of equation. And of course, we can take across the Na. So we've got Na times 1 minus Xa. And then this stays the same. And so we can say Na is equal to C dAb over 1 minus Xa dxa dy. Right. So of course, Xa is the mole fraction and Y is the distance in the vertical direction from the base pointing upwards, right? So it's in the positive vertical direction. So that's Na. And then we can substitute Na into our balance equation. So here's the balance. And from this, we see we just need to differentiate it with respect to Y. We can see that Na is generally a function of Y because there's a derivative in Y here. We anticipate that the mole fraction is going to change vertically. So all this is going to vary with Y. So we, at this stage, we'll just write it as a derivative in Y. So we can say here on this side, it's ddy of Na, and we just substitute for this here. And there's a bit of canceling of minus signs. So remember, this was minus dx dy, and then Na itself has a minus there. So we've canceled that minus. We also have a C here for total concentration. And instead of writing dc dt here, we'll write this as C dx dt. And so those C's can cancel, leaving us with this nice form of equation. So that's our balance at the interior. Were there any questions or comments on that? Just find a place to position this. Any questions or comments on the balance itself? Okay. Then if you look also the update to chapter 3, if you look under the exercises, here's for the slab, we have that at the base, there's no mass transfer there. So the molar flux is 0 at the base where Y equals 0. And so if we substitute for Na, right, if that's the mass flux, then that tells us that the gradient of X in Y is equal to 0. So that's the first boundary condition. Then we said at the surface of the slab, the airflow is rapid, and that implies to us that in the air, we just have the saturation concentration of water. So we know that air does contain a certain amount of water. And if we call that the saturation concentration, then the concentration in the air. So when we say Y equals H plus, that means just above the surface, right? So the slab is H units high. And so looking at a point just above the surface, right? That's why we say the plus. You can think of this as H plus some very small step above the surface. So we just call it H plus. So just above that surface, it's air, and so that's the saturation concentration. what we actually want is the boundary condition inside the slab. And so we say here, we want the concentration where y equals h minus. So just inside of the concrete at the upper surface, this is the right way to reference it. And then because we know that point is very close to the air, then we know that the equilibrium relationship holds there. So if we take the equilibrium constant, which is provided with the question, the equilibrium constant multiplied by the air concentration, then we would get the concrete concentration. And we've just said that the concentration in the air is Ca sat, so it's K is Ca sat. So this is the second boundary condition that we were looking for. And then the last one was just stating that initially we have a certain concentration of water in the slab. And so that's, we just define that to be Ca naught. And it is provided in the question. I think it's something like 10%. So about 10%. And initially we have, excuse me, sorry about that. We have initially at all points y in the slab, but at specifically t equals 0, we have that concentration. So that's our third boundary condition. So those constitute the boundary conditions that that are relevant to this problem. So with the material balance, which describes all the interior points, right? You can think of it as this defines all the interior points in the slab, and this defines at the boundaries of the slab, right? That is then a complete description of the physics of the problem. And then it's just a matter of applying what we know in terms of solving the maths to get a solution. So we'll come to that in the next section, right? We'll look at how to solve these equations in the next section. So for now, we can say that's all the development we can do in terms of the drying of concrete problem. So as we said last time, even though the problem looks nicely, fully specified, we have to do this in stages. And some of you have been asking by email, how do I solve this drying of concrete problem? So we can see we have to do it in stages. So first we've got our material balance. Now we've got our boundary conditions, and then we'll have to look at how to solve it from there. So that's the final step. So what we want to do today is come back to this problem where we have now the flow, so convection and diffusion in cylindrical flow. So we're looking at this again in chapter 2 in case study 3. So we've got the cylindrical flow problem. And let's see if I can get this on one. Okay. So we had covered this, but I think this was the week where there was a bit of student disruption and so on. So we're going to just describe what we said at that time. So in this case, we have our convection and diffusion in cylindrical flow. And we said that generally speaking, there will be variations in T. So we don't know as yet whether there'll be any steady state. So if we don't know there's steady state, we have to preserve the T, the time. We anticipate that there'll be changes in R, because at some stage, it's mentioned in the problem that there's deposition in the wall. So if component A is diffusing on the wall, right, and let's just try and draw it here. And my apologies, I don't have my regular setup, so I might be a little slower in drawing these things. By the way, can you see this screen? So at the moment, I'm looking at, drawing. You should see 2 blocks here. I'm just going to check, can you see those 2 blocks when I do that? Okay, great, thanks. Okay, so if we are expecting deposition on the wall here, then if we imagine, let's see, where's the, if we imagine the fluid enters here, so here's our entry pipeline, and then here is the tube that we are flowing through. We can imagine that our components are going to flow around here, and because they are being consumed on the wall, then there will be a local low concentration on the wall, right? So component A being deposited on the wall means that the local concentration of A will be low. So that sounds a bit contradictory because A is being deposited on the wall, so A should be accumulating there, but now we are saying there's going to be a low concentration. And that's because we are talking about the fluid. So in terms of the liquid fluid that's flowing through here, we have a different phase, if you like. So the wall, we can think of it as a different phase. So A is depositing on the wall, and that's depleting A from the liquid phase. So we have in the liquid phase a low concentration of A, and then on the wall, of course, A concentration is rising. So because of the local low concentration of A in the liquid, there's a tendency for A in the bulk of the liquid to start diffusing towards that low concentration. Okay, so we do expect that there might be radial gradients there. So that's what we can say in terms of R. We do expect that there may be radial gradients. And then if we think about this stream that's entering here, we can see that, let's try and get some room. So we can see that component A is flowing across the space. And we anticipate that as A leaves the fluid and enters the wall, then we are depleting A. So we are expecting that the concentration of A will be dropping as we look down the tube. So that's also then meaning that Z, we expect the concentration to vary in Z as well. So these three variables are relevant. And if that's the case, then we have to choose our finite volume. And we showed that the ring was appropriate in that case. So for the ring volume, we said that the finite volume was 2 pi r delta Z. We said the area in the radial direction. So if you think of, radiating out in this direction, just a second. So if we think about diffusing in this direction, and if we imagine the radius that applies there, right? If we imagine the curved surface that we are seeing when we radiate outwards, then that curved surface will have a circumference of 2 pi r, and it will have an axial distance of delta Z. So this inside area here is our radial, let's call that our radial area AR. So we've got, and we said also, if we imagine a coin, then the curved surface of that coin, that's the area that's relevant here. So the radial area, the area that you encounter when you diffuse radially, that's going to be 2 pi r delta Z, right? And then the other area that you can also see is when you are moving axially. So moving axially and noting that our finite volume is actually a ring. It's not a disk. It's a ring like this. So if you imagine a ring on your finger, right? I don't mean like an abstract mathematical ring. I mean a ring that you can wear on your finger. Then you can imagine there's a flat face of that ring as well. So when we move axially, we are going to encounter this flat face of the ring. And so a way to approximate that area is 2 pi r, the inner circumference, times the radial thickness delta r. So 2 pi r delta r is the area that's normal to flux in the axial direction. Okay. So with those defined, right, and it is useful to, before you jump into the material balance, to just define all those things. So define the volume of this finite space, and then define also the areas that might be normal there. Okay, and let's now look at applying this in our material balance. So we know we want the rate of change of the number of moles in this finite volume. And we can get that by taking the rate of change of the concentration times the volume of that finite volume. And we've already defined what that is there. So that's the rate of change of the number of moles inside of this ring, right? Inside this ring here. So we know that's going to change with time due to axial flux. So here we have two terms for axial flux and due to radial flux. And we have another two terms here for radial flux. This last term is pretty long because we are specifying all the arguments there, but we'll get to that. But these are two terms, just two terms here and another two terms here. And it's two terms for in and out, right? So in the axial direction, we are entering that ring at position Z, and we are leaving it at position Z plus delta Z. So this is the flux at position Z in the axial direction. That's the flux in the axial direction at Z plus delta Z. And then we've defined the area that's normal to that. So delta AZ is that one. So that's in and out flux in the axial directions. And then in the radial direction, we have NAR. So at radial position R, and the area that's normal to that, so that inside curved surface. And then the radial flux out at R plus delta R. And that's at a different, so there now we have to be a bit more careful. So we've got the flux, we've got a flux into the space here. So we've got a flux into the space here. So that's what's coming in. If you like, the fluid that's in the interior of that ring, right? On the inside of that ring, you've got the flux arriving on that curved surface, and then leaving the ring will be at this position. So it's at a greater R position. And we have to acknowledge that the area on that outer surface of the ring is greater than the area on the inside curved surface of the ring. So the area on the outer curved surface, we've called it delta R at R plus delta R. And we know that's also equal to 2 pi R plus delta R times delta Z. So anyway, let's look at, if we look at just this general form here, we haven't specified exactly what these molar fluxes are. And we know we've got that flux expression that we can always refer to, but for now we've just left it in that form. And we've also abstracted out the geometry. We've said a delta V, a delta A, and so on. And we're just quite careful about what area we are talking about. So we have to be very clear about which area this refers to. This is the area that's normal to the Z direction. This is the area that's normal in the R direction, right? So with all that specified, we can now replace our expressions in our balance. So we can just forget about the dNA dt. We know we are accounting for it here. So that's dCA dt times delta V, which we said was this. And then NAZ and area in the Z direction and NAZ area in the Z direction. So those are fixed. But for the flux in the R direction, you've got NAR, and that's the area on the inside. And then you've got NAR, and here we are specifying this will be at the R plus delta R position. And there the area is a bit different. This is at a slightly greater R position as well. So that's the other area, and that's a complete equation as it is. But of course, we'd like to write this more compactly and more usefully in a form that we can solve. So what we can do first is just divide both sides by this factor, 2 pi R delta Z. And we can see that 2 pi R delta R can vanish in both these terms. So both the axial terms easily get rid of this 2 pi R delta R, leaving us with just a 1 over delta Z. And so we've got here NAZ minus NAZ at Z plus delta Z. So that's the axial flux. And then the radial flux, we've got, if we divide by 2 pi R delta Z, the delta Zs are at least going to disappear. The 2 pi Rs, the 2 pi's can also cancel, but the Rs are different. So this R is the same as this R, but this R is not, right? This is a slightly different R position. So we can't cancel that R. we can still say this is a function NA times R, and this is a function NA times R. So when we write it, we can write it that way. This is NA times R, it's a different R, and this is NA at R. So those are those two terms. And then if you take the limits for delta Z going to 0 and delta R going to 0, you can see we get here dCA dt equals ddz of NAZ. And that's a minus because the Z plus delta Z has a minus sign in front. So to swap them around, we need a minus there. And similarly here, we couldn't cancel the R's, so we just keep the R's here, and then it's DDR there. Any questions or comments on that so far? Okay, and then if we just put that together, we can say the molar flux in the Z direction, that's due to convective flow and also due to diffusion. And then the molar flux in the R direction, there's no convection in the R direction, so there's just diffusion. So if we stick in these NAZs and NARs, then that's the balance we get. Okay, so this was a bit of revision on this problem. And I think it's you can say, well, why did we look at this whole thing again? But this is such basic chemical engineering. If you can really understand this, most of chemical engineering is explained in this development. So really spend some time thinking about this. Make sure each term makes a physical sense. There's no single thing on this development that requires memory or some assumption. Everything it can be understood from the very first principles. Okay, but of course, this is just the material balance. So now let's look at the boundary conditions. So any questions or comments there so far? Okay, so let's start with the boundary conditions. And so this is on the slab, and here is our flow in the cylindrical pipeline. So the first boundary condition is that the feed concentration is known, right? In fact, let's just read all of this. So the feed concentration is known. The pipeline is long enough for gradients to die out eventually, right? So that's another very physical thing. All these statements are quite physical. It's not like some mathematical abstraction we're talking about here. Then there's something about a centerline condition. It should actually say centerline symmetry. So we expect that things are symmetrical around the center. We know that there's deposition on the wall, and we know that initially we don't have any A in the tube. So let's look at developing the boundary conditions for the cylindrical pipeline flow. So just taking a minute, please write down your expression for the first one, right? The feed concentration is known. How would you express that? Right, and this one should be pretty quick, right? So I expect you've all written down this expression. So let's just do it here. And oops. Let's see, let's draw it first. So we've got our feed here. So, well, the way we've drawn it, we've got feed into the pipeline here. But let's assume immediately on entering, everything gets well mixed in this direction. Then we can talk about an inlet concentration here. Let's say it's Ca in. So Ca in is the inlet concentration in. Okay, that looks pretty horrible. So let's. So Ca in, that's what we have here. Okay, so that's our inlet concentration. Now, to express that in terms of the variables we've been using for the balance, we can simply say that C Okay, so we can say that the concentration of A at, well, for all time t, for the z position, z equals 0, and for all r positions, right? So this is now in terms of the variables we've been using in our balance. So for all time t, but specifically at z equals 0, at the front edge of the pipeline and at all radial positions, we have the known inlet concentration Ca in, right? So we'd call that our first boundary condition. Okay, so that's the first one. The inlet concentration is known. For the next one, excuse me, the pipeline is long enough for gradients to die out eventually. So take a minute and just sketch out your the way that you would express this in terms of the balance we've defined. So this one is, if it's saying it's long enough for gradients to die out eventually, so that means by the end of the pipe, we don't have a gradient. So if we were to sketch that, we would say, generally speaking, we know that, generally speaking, we know that the concentration is varying down the pipe. So if we were to plot the concentration down the pipeline, so let's say we have something like this. So this is how concentration is varying in the z direction. And we are saying the pipe is long enough. So the pipe being long enough implies that although something is happening out here, right, in terms of A being deposited onto the surface, it might be the case that we reach a stage where we've so depleted the fluid in the pipeline that the deposition of A is no longer significant. And so we now have, we don't have much further deposition happening. And so by the time we reach the exit, there's no gradient here. And of course, we are talking very axially here. We are talking about variations axially. And so that means the axial gradient has died out. So the way we can express that is to say dCA, and it's the axial gradient, so it's dz. And we can say specifically at position z equals L. So let's see if this works. So we are saying for all times t, specifically at z equals L, and for all r positions, then that's equal to 0. So that's how we express the end condition, which is stating that gradients have died out by then. So there's no gradient in the z direction at the end of the pipe, z equals L, right? So that's our second boundary condition. Any questions or comments on that? Okay, so that's the second boundary condition. And then the center line condition. So that tells us, or what this should say is the symmetry at the center. So if we think about our pipeline, if we think about the radial gradients, and let's try and draw that again. So let's imagine we've got a, let's imagine the radial gradient through that space. So let's just draw it like this. Oops. Let's change this and this. So if we imagine the concentration as it's varying across the pipeline in the radial direction, right? The concentration is varying radially. And we know we have a lower concentration near the wall because A is being deposited on the wall. Still, the same thing is happening on all sides, right? If we take a vertical slice through this pipeline, then we'll see a low concentration at the top edge and a low concentration at the bottom edge. And near the center, A is not being depleted, so it will have a higher concentration. So if the same thing is happening at on either end, right, of the slice, remember we've took a vertical slice through this pipeline. If the same thing is happening at both ends, then it means that near the center, that there is a symmetry in this direction. So it's symmetrical about this point. Imagine a line running through the center here. Oh, well, we don't have to imagine it. Let's draw a line through the center here. So this is a line of symmetry. So, or a plane of symmetry. Imagine a flat plane. So the same is happening above and below. That means at the point, at the center point here, we can see that the gradient is going to be a 0. So it might be non-zero at all these points, but because the same is happening on both sides, they kind of cancel each other out at the center point. So we can say at the center line, we have a radial symmetry, and we're going to express that in this way. We'll say dCA dr, and this has to be specifically at the center. It doesn't apply anywhere else. So at the center, and of course there are multiple locations of the center. That's more like a center line. So at the center line, in other words, at all instants in time, at all axial positions, but at the center line. So at the center line, r equals 0. Then we have radial symmetry. So that's the third condition, radial symmetry at the center. Okay, any questions or comments on that? Okay, so we have symmetry. And then, of course, we have the deposition condition. So we said that at the surface of the pipeline, A is being deposited there. And we were also given a deposition rate. We said J equals KCA. So the deposition flux was J equals KCA. Excuse me. And we know that's equal to the molar flux in that direction. So we can say NAR. NAR is the flux at that location. So at that location, we can say that's equal to, this applies to all instants in time. It applies to all axial positions, but it applies only at the radial position where R equals R, right? The center, not the center, the inside surface of the pipe. So if we define the inside surface to be a capital R, then that's the location we're looking at. So the axial flux there is equal to KCA. And in this case, I think this is the case of equimolar counter diffusion. So just wanting to separate these a bit. So this is boundary condition 3, or what is it? No, boundary condition 4, I think. Okay, so this is boundary condition 4. This is boundary condition 3, and this one was 2. And we had labeled this one 1. So the fourth boundary condition says this. And so we have that we then have to just think about the flux here, the molar flux in the radial direction. So we did talk about this. So we had specified the molar flux in the radial direction for this case. So if we just go back here to our balance, we said the flux in the radial direction was equal to this. So we can just replace that NA by this term. So we can say our fourth boundary condition is then that minus C dAB times dCA dr, and this has to be specifically at TZ and R. TZ R equals R. That flux is equal to the deposition flux, which we said was KCA. Or not, we said, the problem said this. The problem stated that there was a certain deposition constant. Maybe let's make that more explicit. So there's a certain deposition constant which depends on the concentration. And we have to realize here, this is the concentration at that wall. So we can also specify here for all time, for all axial positions, but specifically at the wall. So this is a specific concentration. And so that concentration times the deposition constant, that's the deposition flux on the wall. And then this is the flux, the molar flux that's moving towards the wall. And these are two different, how can I say, two different phenomena, two different events. This is the act of the deposition onto the wall, and this is the act of flux towards the wall. And we are saying these two are equal. So this is not just an equal sign as if there's some mechanical operation and then we get that. We mean different things when we look on either side here. So we know that there's a molar flux towards the wall, which is the result of a deposition onto the wall. So that equal sign is our statement that those two fluxes must be equal, right? So the rate at which we are depositing onto the wall must equal the rate at which we that A is fluxing towards that wall. And so that's our fourth boundary condition. Any questions or comments there? Okay, everyone's very quiet today. Yeah, you all there and listening? I must say it's much harder teaching like this than in the classroom. I so enjoyed the brief 2 weeks we had just in person. So yeah, it's much harder for me. So yeah, the questions are much appreciated as they come up. So that's our fourth boundary condition. And then we still have one to go. So in our in our list, so we've gotten here. So the last one says the initial condition assumes that there's none of A initially in the tube. So that's pretty straightforward. If we don't have A in the tube, the concentration is 0 everywhere, and that applies only initially. So we can say here, I guess we can call it boundary condition 5. But as we said before, when it's time, and if it refers to the first instant in time, then we have the special name for this boundary. We call it the initial condition. So in this initial condition, we say the concentration of A and the concentration of A initially, so T equals 0. And this applies at all axial positions and at all radial positions. And we have none of A initially. So we say that's 0. And please be a bit careful with the difference between the initial concentration and the inlet concentration, right? This is the concentration that's being fed in at position Z equals 0. That does not mean the same thing as the initial concentration inside of the tube. So going back to the drawing, we have this whole tube here. We can still define the concentration of A at all points in the tube, even initially. So even initially, before we even started feeding anything here, we have certain we can define a concentration in the tube. It just so happens it's a 0, but that's a different point that the concentration happens to be 0. We can always define a concentration at all points in the space, and that's generally different to the concentration that's entering here, Ca in, where Z equals 0. And I'm saying this because you find in certain textbooks that the Ca naught, they sometimes use Ca naught for an inlet concentration. And we need to be very careful that our Ca naught, which happens to be 0, so we can say here Ca naught, we can give it a special name, Ca naught. This is generally different from your inlet concentration. Okay. Any questions or comments there? So now we have enough boundary conditions, right? If we have a look at our balance, remember we had a way to figure out how many boundary conditions we needed. We said we would look at each of the independent variables, right? T, Z, and R, and look at the order of the derivative. What's the highest derivative in each dimension? So in time, we only have one derivative, a first order derivative. In Z, we have a derivative of a derivative. So this term will give us a first order derivative, but this term will give us a second order derivative. So we count it as second order with respect to Z. So we need two boundary conditions for that. And here for R, we have a derivative, again, of a derivative. So this is a second order derivative in R. So we have 1 plus 2 plus 2 is 5. And we now have 5 boundary conditions. And so at this stage, we are just going to say, in principle, then, we have enough information to solve these equations. And we'll look at the solution in the next section, in the next part. So how to solve these equations is coming up next. At the moment, we've carefully developed the interior material balance, and we've developed the boundary conditions. So we're ready for that next part next. Okay, any questions or comments there? All right, now let's look at the third one. So our particle, our diffusion from a spherical particle. So here, and by the way, these 3 case studies, they do give us a nice variation. Of course, you can see the geometry is very different, right? The first one was a slab. It has rectangular geometry. It has X, Y, and Z. The second one, flow in a pipeline, it has cylindrical geometry. So R, Z, theta. We didn't really talk about theta, the angle, but R and Z, that's what we emphasized here. Then the third case has a spherical particle. So it's just R and 2 angles. And here we'll ignore the 2 angles. But I'm trying to say, we've got the 3 main types of geometry across these 3 case studies. We are also seeing a difference in the type of molar flux. So in the first case, in the drying of concrete, we have a flow through a stagnant medium. So the concrete itself was stagnant and the water is diffusing. So that's a stagnant flow. In the second one, we have equimolar counter diffusion. And then in this third case, we are talking about flux. So this is neither equimolar counter diffusion, nor is it stagnant flow. So A and B are diffusing in this case. So we had developed the material balance before for this. And yeah, it's 9:25. We would normally take a break for 10 minutes. I'm not sure with this remote teaching, shall we take a break there? Okay, let's take a 10-minute break. So we'll continue at 9:35. Okay, welcome back, everyone. So we're now looking at diffusion from the spherical particle. And let's see, are we still recording? Yep. And we have this reaction happening on the surface. So it's a spherical particle that's suspended in some gas or liquid. And we have this reaction occurring on the surface. So 2 molecules of A are giving us 3 molecules of B. And we can imagine that the molar flux of A, so 2 molecules are entering and 3 molecules are leaving. So we have more A diffusing towards the particle than B leaving it. So we pick out certain things like that as we read through the problem, which we'll park that, and when we come back, we'll be able to use that. So we can see clearly that the concentration of A in the fluid around the particle is going to change in the radial direction. So looking radially away from the particle, we can see that A is being consumed on the surface. So locally near the surface, the concentration of A is going to drop. So if we draw that, I guess let's do a new one. So we've got a particle. And this is suspended and this is a solid. So we've got a solid particle suspended here. And the solid particle is suspended. And we've got component A that's in the bulk phase here. So we can say component A is in high concentration in the bulk out here. And as A encounters the particle, it gets consumed on the particle surface. So we expect in the fluid next to the particle, right, immediately adjacent to the particle, we would have a low concentration of A there and a higher concentration in the bulk. So we could sketch that as follows. We can say there's a high concentration here and a low concentration here. So it might be something, maybe let's draw it like this, or yeah, let's maybe use a second order type of. Okay, so let's say that's the kind of concentration we expect, right? Consumption at the surface means the concentration will be lower there, and then in the bulk, it's a higher concentration. Let's get a sense for the scale of things. In particles of this nature, we often have a very small particle. In chemical reaction engineering, we are often talking about micron-sized particles. And so the scale here could be as small as microns. So this distance might only be on the order of microns as well. So even though we are talking about a fluid and a particle, we have to think also about how far such differences extend. It's not that we are going to approximate anything by saying all this. It's actually in the next section that we'll take advantage of this. But for right now, if we just think of the scale of things, particles are small things. In a chemical reactor, you can have micron-sized particles, you can have centimeter-sized particles. Centimeters would be pretty big for a chemical reactor. But anyway, so these variations, right? There's a large bulk of A, and so there's some bulk concentration, and it sometimes takes over a short distance, we have some variation here. But these variations are very important because that tells us how a single particle behaves. It tells us what the reaction rate might be for such a particle. And fine, you might have very tiny particles, dust-sized particles, but you might have a ton of such particles in the reactor. So if you have a ton of particles and near each one, there's this concentration variation, then that's going to influence the reaction rate. So the productivity of your reactor might change significantly when you look at the variation of the concentration there. So that's why it's so important for us to be able to develop a balance and understand how the concentration is changing near that particle. It might totally underestimate the productivity of the reactor if we are not able to do this properly. So looking at the balance there, we've talked about radial variations. We can also talk about angular variations. So if we were to just sketch the radial change here, so we would define the radius from the center looking out, right? So you've got a center, and we'll call that the radius r. So you've got a center, and we can define any radial position away from that center. It wouldn't make sense to talk about any radial positions before the surface, inside the surface, because we are wanting to balance what's in the fluid. So we are not balancing changes in the particle. We are assuming this is a solid particle, and we're not interested in diffusion changes on the inside of this particle. We are only interested in changes in the fluid here. So we maybe let's do some labeling. So we can call this radial position 0. Oops. Radial position 0 here. This is radial position capital R. And we are writing a balance looking at some radial position lowercase r. Right, so we want to know, how does the concentration vary away from the particle? And we do that by drawing a shell here. So we are only considering the r as the variable. And so we are taking two positions, r and r plus delta r. And when we do that, if we imagine the approximate volume of the space, right? Let's imagine the finite volume. So I guess we might as well draw it. Yeah, see, it doesn't show on your side, but on my side, yeah, this I always have to drag that zoom thing out of the way. And oops. So we are picking a radial position. Oops. So we are picking a radial position, something like this. Oh, these little helpers. Okay. Yeah, thank you. So we are picking a radial position there, and then we'll pick similarly another radial position. Let's say another radial position at r plus delta r. And so we can draw a line like that. So we can say, here's the other radial position at r plus delta r. Just write it as a dr. Okay, so the volume, the finite volume of interest to us is this space. So between these two lines is the finite volume of interest. We can see that the inside area, right, it's a sphere. We know the surface area of a sphere is 4 pi r squared. So the inside area, 4 pi r squared, and then times this thickness delta r, that's an estimate of the volume of that space. So looking here, we can say the volume there, 4 pi r squared, the inside area times the thickness delta r, that's an estimate of the volume. We can also say that we are expecting diffusion in this direction. And actually A is diffusing in from outside, it's diffusing in, that's what's actually happening. But when we define our spatial dimension as pointing out like this, right, we are pointing from the center out away from the particle, then we write the balances as if it's fluxing in here and fluxing out there, right? This is a very important point, which we didn't really talk about. But when we define our variable, our direction, we always define where the zero is and in which direction it's increasing. So clearly the most logical choice for R would be the center is here and we are pushing out away from the particle. So whenever we write our material balances, we regard flux in at the lower value. So even if it's Z, we always wrote in terms of Z minus Z plus delta Z. So here we'll always write what's coming in is at R and what's going out is at R plus delta R. And then the fact that the flux is in the opposite direction will just change the sign of NA. So if it looks confusing, we know A is fluxing in. Why are we writing as if it's fluxing out? It's because that's the general way to write these balances. And the sign of NA will take care of the actual direction for the balance. Okay, just to check any questions or comments on that. So quiet today. I'm actually getting worried. Okay. So we have those 2 points, and in the notes you'll also find this is developed here. So we've defined the volume of this finite volume. We've defined the area of this finite volume. The area that's normal to flux in the R direction. That's your delta AR. And so we can write the rate of change of moles in this finite volume is equal to the concentration times the volume of that space. So dCdt times the volume of that space. And then we've got the flux in. So the molar flux at position R, so coming into that sphere, times the area, the 4 pi R squared. And then fluxing out, we can say this is NA at R plus delta R. And the area that we are fluxing out of is at a different R position. So the area is bigger there. So if you look at this outer sphere, that has a larger area than the inner sphere, of course, just because the radial, it has a different radius. So that's what we have. So the flux in and the flux out. And then, of course, we'll want to, first what we do is, here we abstract this variable R. So we rewrite this R as R at position R. And then we rewrite this, this R plus delta R as also R, but at R plus delta R. So you can say the radial position at R plus delta R. It's a bit of a strange way to say it, but this is all just R, right? This is also just an R, but it's a different R's. Okay, so we abstract it that way just to emphasize that we have NA times R squared and we have NA times R squared. So that's effectively the function. Because what we would do next is divide everywhere by 4 pi R squared delta R. So it cancels on this side. And then the 4 pi can cancel in both terms. The R squared can cancel here, but it can't cancel here because it's a different R. So we eventually have to preserve the 1 over R squared and the R squared on the inside. And so that's the general balance in terms of variation in just R, not in theta 1 and theta 2. Yeah, that's our balance. And now what we want to do is substitute for the molar flux here. We don't like an equation like this with 2 unknown variables, right? Ca is the dependent variable. Na is also a dependent variable, but we can re-express it in terms of Ca using our statement for molar flux. So for our molar flux, that's the general form that we have, this time just in the R direction. And if we look at the surface, right, on the surface, we can see that 2 moles of A come in and 3 moles of B go out. So the molar flux of B, the magnitude of the molar flux is greater than the magnitude of the molar flux of A. And we can see that we get 3 times B divided by 2 times A. So we can say the molar flux of B is 3 divided by 2 times the molar flux of A. And we include a minus sign because these are fluxes in the opposite direction. So A is always fluxing towards the particle because it's being consumed there. The local concentration is low there. So we are always diffusing from high to low. So A is always fluxing towards the particle. B is formed on the particle's surface. So the concentration is high near the particle. So B is always fluxing away from the particle. So towards the particle, away from the particle. So the minus sign has to be there. So that's flux, and then we can substitute for NB in here. And so now we've got Na is XA, and then here minus 3 Na. So these Nas give us on balance minus a half Na, and the rest applies. So we've got the diffusion part here. And so we can rewrite this as minus a half Na. So that's there. And the same term here. And then we can take this across to the other side, right? We can group it with this Na. So this is Na, 1 times Na. And then we've taken this minus a half across here. So it's plus a half times Xa. So that's that term. And then this is the leftover term. So the diffusion part is here. So now we can say the molar flux of A is minus dAB over 1 plus Xa over 2 times dCA dR. So that's our expression for the molar flux. And then we can substitute this into our balance expression here to get rid of this NAR. So now we have finally this form. So we've got dC dt equals 1 over R squared ddr dAB over 1 plus XA over 2 times dCA dR R squared. What I would prefer to do here is remove this concentration, so that, because we also don't want a new variable. We've got an XA here. We can't get away from this XA. Let's rewrite this in a CA. So just going to edit this quickly. Or rewrite this part. So on this side of the equation, we'll extract a C. So we'll say C times dxa dt. And on this side, we've got a C here. So this C we'll write in terms of X, and we'll need to extract a C here. So let's just check that renders properly. Yeah, under our material balance, this is a spherical particle. So just looking at these two equations, I've just acknowledged that this concentration is the, so Ca is the total concentration C times the mole fraction of A. So C times Xa equals Ca. And then here, we haven't disturbed any of this, but this Ca, we can rewrite it as total concentration C times Xa. So we can split off a C here and rewrite this part as dxa dr. So these two C's can cancel, and that leaves us with the better form in just one variable. So it's going to look like that. See how difficult it is to write these notes in the code and all that. And now you won't even talk to me. Yeah. So here's your material balance. Here's your spherical particle. And here, so we can see in this balance now, we've got just one dependent variable, Xa. We've got two independent variables, T and R. So this is quite a friendly form of the equation for the material balance for our sphere. Any questions or comments about this balance? Okay, so that's the balance. And now let's look for the boundary conditions. So Yeah, in the case of the surface reaction on the spherical particle, so that's referring to in chapter 2 what we just looked at. So now in chapter 3, we want to develop the boundary conditions. So we start off the surface reaction. So just take a minute and write out yourself what you think the surface reaction should be written as. And just a kind of hint towards that, the surface reaction, a reaction rate can be written in terms of like a reaction flux. So if we say something like this, if we say the reaction rate, so we can say the reaction rate RA, and for area-based rates, we use a double dashed in reaction engineering. And let's just say this reaction is K times CA squared. K times C. We do this. So our reaction rate minus RA. RA, okay. So our reaction rate is KCA squared. And this is a consumption of component A. And this is going to have units of moles per second per square meter. So this is an area-based reaction rate. Okay, so this is per area of particle. And we need the double dashed for this one. Let's see. To emphasize, so when it's double dashed, that's an area-based rate. Okay, so you've got this area-based rate. So write out on the surface what your boundary condition would be. Okay, so if it's an area-based rate on the particle surface, this is effectively a flux, right? This is the reaction flux. So what we can say then is on the surface, so BC1, on the surface, we have, we can talk about a flux on the surface. So we can say there's a molar flux of A in the R direction, in the R direction. And this applies for all time at the specific radial position R equals R. So the flux there must equal the consumption rate. So the rate at which A is being supplied to the surface must equal the rate at which it's being consumed. So minus RA, minus RA double dashed. Yeah. So your flux on the surface equals the reaction rate. And like we had before with the deposition rate, these are two different phenomena. And we are saying that they become equal at a kind of steady state, right? At steady state, you are supplying as much A, right? A is fluxing towards the surface as fast as A is being consumed on the surface. So this is the consumption rate on the surface, and this is the rate at which A is fluxing towards that surface. So that's a statement. That's how we interpret that boundary condition. And then we can say that that flux of A, NAR, we can write we have an expression for that. So we had determined that NAR was equal to this thing. So we can say minus DAB over 1 plus XA. Let's do it. So minus DAB over 1 plus XA over 2. times dCAdr times dCAdr, that's equal to Ra double dashed. So like this is fine. This is an acceptable version of our boundary condition. So that's our first boundary condition. Okay, then let's look at the next one. So the next boundary condition, it just says the bulk concentration. So for that, it basically means that there does exist some, in that whole fluid, there is some bulk concentration that we know near this little particle, the concentration is varying. But in the bulk, far away from the particle, there does exist some concentration. So we can state that simply as, so BC2, I guess, we can say here, the concentration of A for all time at some distance away from the particle. And this will be infinitely far away from the particle, that there is some known concentration in the fluid, which we'll call CAB, the bulk concentration. So this statement we can read as, if we look far enough away from the particle, then the concentration is just the bulk concentration. So we regard that as another boundary condition. Okay. So we have those two. And then we have the initial condition as well. So for the initial condition, well, maybe, yeah, I'll give you a minute to try that out. What do you think that initial condition would be in terms of CAB? So write down the initial condition for the concentration of A. Okay, so for this initial condition, we'll say the concentration of A initially. So if it's initial, then T equals 0. And this applies to all radial positions. So initially, the particle, you can think of just dropping the particle into the fluid. So like a liquid, you just drop the particle in and it starts to consume A on the surface. But initially, the particle had just entered. There wasn't any time for A to really be consumed or anything like that. Then the concentration everywhere is equal to CAB. So not just far away from the particle, but near the particle as well, you have that initial concentration. And so we have three boundary conditions. And if we look at the balance, we can see that we have two independent variables, T and R. For T, it's a first order derivative. For R, it's a derivative of a derivative. So it's a second order. So we need two boundary conditions for R and one for T. And that's what we have. Right? We've just done the T boundary condition or the initial condition. And we've got far away from the particle, we've got one condition. And we've got close by the particle, we've got a different condition. So those are three extra pieces of information, nailing down a solution. And so this plus our general mole balance will let us get a solution and solve for XA as it varies in R and T. Okay, any questions or comments there? All right, so work through these three. These are, if you like, very typical cases in all of chemical engineering, right? Flow in a pipeline, deposition onto walls, components drying out or leaving a space like with a slab, or reaction on a surface. These are core chemical engineering things. So be sure you are able, number one, to get the right material balances, and number two, to get the right boundary conditions. That's all it is. Everything else you see in chemical engineering will just be applications of these basic types of things. All the design equations, everything, it's all based on this. So understand these things well, and you have solid ground to work from. So those three case studies, we will start looking at solutions towards them. But I want us now to have a look at the so-called film theory. So film theory is, you could think of it as a way to simplify our boundary conditions. So in film theory, we are thinking about the fact that near certain elements, so near certain interfaces, that the changes happening there are happening over a small enough space that it doesn't really make sense to go and solve an equation for the whole space. So that sounds a bit abstract, but let's think about our spherical particle. We said this particle could be very small. Let's say it's even on the scale of centimeters, which is actually huge in reaction engineering, but let's say it's a centimeter. And let's say it's sitting in a cubic meter of some reactant. So it's a big space and we have a particle in there. It's 1 centimeter in size. Now, do you think the gradient, right? Remember we said there's a concentration profile that will look like this. Do you really think this is going to go all the way across 1 meter of that space, right? This change is only going to happen in a small region close by this particle, right? It's on the order of maybe 0.5 centimeter where this change in the concentration exists, right? Outside of that space, you would have you would have the bulk concentration. You'll have something like this, right? So, oops. Let's see. So you are going to end up with, in the bulk fluid, you'll have some concentration. Then near the particle where the action is happening, you are going to get some changes. So the proposal in film theory is, well, why go and write a balance on the whole reactor, on this entire cubic meter scale here? Instead of doing all that, why don't we just define a small region where the action is happening and then figure out what that variation looks like? So that's a film. We define the film to be the region in which the majority of the action is happening. So in film theory, we define a small region and we call that region delta. So so a lowercase delta, right? Not the triangle kind of delta. Where's my little pen? So this Zoom thing gets in the way. So here's my little pen. So we define a delta to be this space, right? Let's say we define this delta. So delta, it's a lowercase delta. So you know the symbol, a delta. So in this delta, we have the space in which all the action happens. And so we will simplify our development by saying, yes, we know this is a curve and we, in principle, have to apply diffusion and everything. But let's just be chemical engineers for a second and just say straight line. I'm just going to stick a straight line across the space. So that's going to be my way of simplifying this. So the whole of film theory is just about simplifying all the action into one basic idea. And you can see here that's going to help. The straight line, it does capture all the important features. We don't really need to know, oh, the curve actually curves this way here and it curves that way there. We just want to know what's the rate of transfer across this space where we are close enough to the particle. So that's, it's not like some new concept. It's just a way to simplify the expression of all the actual variations. So I guess here it's talking about the membrane example. So if you look back in the first case study, in the membrane example, we had that across the membrane, there was a concentration difference, and that led to some variation in the concentration profile in one of the cells. And so we could define our film here. You can say most of the action is happening in this little film. And maybe this is just a few millimeters, whereas maybe the cell is meters long. So in this space, we can say, yes, that's the actual variation in concentration, but we are going to simplify that down and just draw a straight line. And we are also going to define a constant here. We are going to call this the mass transfer coefficient. So film theory, when you see mass transfer coefficient, that's associated with the film theory. Because we've defined a film, we can say across that film, there are two concentrations that matter. So the left side and the right side. So here we have defined Ca2, I guess this would be naught plus. So just on this side of the membrane, we have a point here. And then in the bulk, we have a CAB. So according to film theory, the driving force is the difference between those concentrations. And we define another constant, the mass transfer coefficient. So Kc, the mass transfer coefficient, times this difference is going to give us our molar flux. So that's the molar flux in this space. And of course, we still have to be consistent with the strictly defined flux. So this is what we had defined before. We said that in this case, I think this was equimolar counter diffusion. So we get this form, right? So Fick's law, this is strictly what's happening. This is according to the, this is according to the physics of the problem. There's diffusivity and there's diffusion gradients, and that gradient actually varies across this. It's not a straight line, it's more like a curve, like on this side. So that's true, but we can just be chemical engineers and say, oh, I don't like dealing with such complication. I just want to subtract two numbers. I just want a fudge factor here. That's what film theory is. So the disadvantage here is we don't actually know what this Kc is. But as chemical engineers, we give ourselves that freedom. We say, I'm just going to define this constant and hope for the best. Well, we don't just hope for the best. We say, okay, if this is the strictly defined one, then surely we can equate them. So if we equate these two, right, it's the same flux. So equating them, we can say this flux, the strictly defined diffusion flux, that must, if we were to simplify this, if we were to get a straight line difference here, never mind that it's not straight, but if it was straight, then we could say, well, I've already defined this distance. I've said that's a delta, that's my film thickness. And I've said there are two concentrations here. So the two concentrations divided by the delta, that's going to be the gradient dc dx, right? The gradient dc dx. Find that varies in the general case, but here we are saying simplify it, make it a straight line gradient. And so the diffusivity is that. So that's what we have. And we've just said, well, then just make that equal to a mass transfer coefficient that we don't know and the same concentration difference. So we can see the same concentration difference on both sides. So we can just cancel them. So canceling these two, we can see we're left with Kc equals dAe over delta. So that gives us the relationship between the strictly defined diffusivity, our wishful thinkingly defined mass transfer coefficient, and the film thickness. Now, that film thickness is somewhat complicated, right? Let's go back to the strict case. So we know that in these gradients, that these gradients never actually die out. Fine, near the point of action, you've got a sharper gradient, but as you go away, this gradient dies out slowly, but it never does die out because the gradient going lower and lower means the diffusion flux goes lower and lower. So because your rate of transfer is going down, and that's what's driving the flux, that's what's driving the gradient to even out, the two don't cancel each other out. And so we get what looks very flat, but is never perfectly flat. So if that's the case, you could say the film goes on to infinity, right? You could say, well, the action is always happening, even if you've got a micron particle sitting inside a 20 cubic meter tank, still that whole tank is affected by that one speck of dust. And that's strictly true, but it's true in the way that if you think of Newton's gravitational attraction, right? Fine, the moon is exerting a pull on the most furthest galaxy in the universe. But of course, that pull is so small that we might as well only count the gravitational attraction near the moon, probably only close to the Earth. So we need some criterion. We need to say, excuse me, we need to choose a criterion. We need to say where enough is enough. So we propose as chemical engineers that we are going to define the form to be where we are at 99% of the bulk concentration. So that's a purely arbitrary number, but we do that, right? So as chemical engineers, we say enough's enough. I'm at 99% of the bulk at this point, at this location. So that's my film thickness. So that's how we can get that delta. Excuse me, sorry about that. So we define this delta to be the distance away from the interface where the action is happening. It's the distance away where the concentration becomes equal to 99. Excuse me, 1 second. I'm just going to drink some water. Okay, sorry about that. So we are defining this delta to be the position where our concentration becomes 99% of the bulk concentration. So let's draw this a bit differently. So let's pick a different color. So if we integrate this line, and if we know the bulk concentration here, then we just take 99% of that, and perhaps that's this position. Then we say the form that applies is the distance from the surface here to that position. And then that's a finite distance. Maybe this is 5 microns or something like that. So that's going to be our form thickness delta. And then we have a finite number here for delta. We have a diffusivity, and that defines a mass transfer coefficient. So that's how we can really simplify our boundary conditions, right? Through proposing a form, right? And of course, this form is an imaginary position. There's no actual form, but it's just the place where we imagine enough of the action to have happened. So that's a form. And we also want to deal with a much simpler form. So to avoid the derivative, we'll just take a difference and multiply by this coefficient here. Okay, so that's the form theory. And perhaps as an exercise, look at the boundary conditions we developed today and see how to use a form theory to simplify them. Any questions or comments there? All right, if not, that's it for today. See you next time.